Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's video, let us discuss some of the theorems on eigenvalues and eigenvectors. In today's class, let us first recap the eigenvectors and eigenvalues and eigenspace. We will discuss about eigenspace and we solve some of the problems on eigenspace, and later we prove two theorems, one on eigenvalues and other on eigenvectors. So this is our today's class map. Let us first recall the definition of eigenvectors and eigenvalues first. Eigenvector. An eigenvector of an n by n matrix A is a non-zero vector x such that Ax is equal to lambda x for some scalar lambda. So when an n by n matrix A is given to us, then a vector x for which Ax is equal to lambda x for some scalar lambda, those non-zero axes, non-zero vector x is called eigenvector. This is obvious for zero vector. A into 0 is 0 into some lambda. So we are not interested in zero vectors. So non-zero vectors such that Ax is equal to lambda x, where lambda is a scalar, are called eigenvectors. And this lambda is the eigenvalue. A scalar lambda is called as eigenvalue of A if there is a non-trivial solution x of Ax is equal to lambda x. If we are able to find a solution for this one, a non-zero solution, then we can say that lambda is eigenvalue. Here the x should not be a zero vector. Lambda can be 0, but x should not be zero vector. For example, for a if we can find a vector x such that Ax is equal to 2x, then we can say that 2 is an eigenvalue if that x is not a zero vector. So such an x is called an eigenvector corresponding to lambda. And eigenspace. Today's topic is eigenspace. Lambda is an eigenvalue of an n by n matrix if and only if the equation A minus lambda ix is equal to O. We have seen in the earlier class that Ax is equal to lambda x implies Ax minus lambda x is equal to O. Since lambda is a scalar, if we take x as common, that will become A minus lambda I times x is equal to O. So if this equation has a non-trivial solution, then only lambda is an eigenvalue. So this equation has a non-trivial solution when lambda is an eigenvalue. So the set of all solutions of A minus lambda I x is equal to O is the null space of the matrix A minus lambda I. So if I take this as B, A minus lambda I is B, then the equation will be as Bx is equal to O. So that is a homogeneous equation. Bx is equal to O. The solutions for that system of matrix is null space of P. So here my B is A minus lambda I. So the set of all solutions of A minus lambda I x is equal to O is nothing but the null space of the matrix A minus lambda I. So A is a matrix and I is identity matrix which is multiplied by lambda here. So A minus lambda I is another matrix. So we can easily find out the null matrix, null space of this matrix easily by using the methods we have discussed in the previous classes. So that null space will be a subspace of Rn, and that subspace is called the eigenspace of A corresponding to lambda. So for each lambda, the eigenvalue of a matrix A, there will be a set of eigenvectors which will be a subspace of Rn, and that subspace is called as eigenspace of A corresponding to that eigenvalue. So for each eigenvalue lambda, we can find an eigenspace. The eigenspace consists of the zero vector. So obviously in the null space, zero vector will be there. So eigenspace is null, that zero vector union all other eigenvectors corresponding to lambda. So in addition to the eigenvectors, zero vector is also available in eigenspace. Otherwise, it will not be a subspace. So every eigenspace of a matrix A is the set of all eigenvectors corresponding to a eigenvalue lambda and the zero vector. So zero vector is the common vector in all the eigenspaces. So let us solve a problem related to eigenspace. Let A is equal to 4 minus 1 6, 2 1 6, 2 minus 1 8. An eigenvalue of A is 2. One of the eigenvalue is given here. This matrix is a matrix of 3 by 3. So it will have 3 eigenvalues, out of which one eigenvalue is given to us. Find a basis for the corresponding eigenspace. So we need to find the eigenspace corresponding to this eigenvalue. So to find the eigenspace, we need to find the null space of A minus lambda I. Here lambda is 2. So we need to find the null space of A minus 2i. For that, first let us calculate what is 2 minus A minus 2i. So this is A minus 2i. Since A is a 3 by 3 matrix, we are multiplying 2 with I3. So the identity matrix of order 3. So 2 into 1 0 0 0 1 0 and 0 0 1 is, if you multiply that with 2, you will get 2 0 0 0 2 0 0 0 2. So we are subtracting this from A. So 4 minus 2 is 2. Remaining two elements are same, minus 1 and 6. And 2, 1 minus 2 is minus 1 and 6 minus 0 is 6. 2 minus 0 is 2, 1 minus 1 minus 0 is minus 1, 8 minus 2 is 6. So this is our A minus 2i. Here we can observe that all the three rows are equal. So the augment matrix. So to find null space of A minus 2i, we need to construct an augment matrix A minus 2io. So this is our augment matrix in which zero entries are added in the last column. So by elementary row operations, this can be converted into echelon form and reduced echelon form. Here, since all the rows are equal, we can simply subtract one from another. R2 goes to R2 minus R1, and similarly R3 goes to R3 minus R1 will give the 0 rows. R2 and R3 will become 0 rows. So this is our reduced echelon form. So at this stage we can say that 2 is an eigenvalue of A since this matrix has a non-trivial solution. Since all the rows does not have a pivot, so we can say that, and the columns are also linearly dependent. So we can say that this system of equations has a non-trivial solution. That is a solution other than zero solution. So it is confirmed that 2 is an eigenvalue. Here it is given that 2 is an eigenvalue, but even if you are asked to check whether 2 is an eigenvalue or not, by seeing this echelon form, we can say that 2 is an eigenvalue. Since A minus 2i into x is equal to O has free variables. So we can convert that matrix equation into an equation form, and the equivalent equation is 2x1 minus x2 plus 6x3. Since it is 2 here, 2x1 minus x2 plus 6x3. And this can be written as x1 is equal to x1, 2x1 is equal to x2 minus 6x3, and x1 is equal to half x2 minus 3x3. So the vector x1, x2, x3 can be written as x1 can be replaced with this relation half x2 minus 3x3, and here x2 and x3 are free variables, so they are kept as it is. That is equal to x2 times 1 by 2 and 1 and 0 plus x3 times minus 3 here. So in the first row, minus 3 is the coefficient, that's why it is minus 3. In the second row, x3 is absent, so it is 0. And in the third row, there is x3, that is so it is 1 here. So this vector x1, x2, x3 can be written in this form. x2 times 1 by 2, 1, 0 plus x3 times minus 3, 0, 1. So the eigenspace is equal to span of these two vectors. Here, this is in the form of C1 V1 plus C2 V2, where these two are scalars. Instead of C1 C2, we have x2 and x3. So it is a linear combination of these two vectors. We can also observe that these two are linearly independent, since one is not a multiple of other. So these two vectors, V1 and V2, let us say, these two vectors will form a basis for the set of solutions. or we can say null space of A minus 2i. So it can span the eigenspace. So eigenspace is equal to span of these two vectors. That is equal to span of, we can multiply the first vector with 2. 1, 2, 0 for simplification. Though the vectors are different, the set spanned by these vectors is same. Since any vector produced by these two vectors can also be produced by these two. So a vector which can be a linear combination of these two vectors can also be represented as a linear combination of these two vectors. So both are same. Here we can observe that since there are two vectors and these two are linearly independent, so this is the basis. The set is the basis for eigenspace in which there are two vectors. So dimension of eigenspace is 2. This can be written in other way also. So we need not to have same vectors every time. So the same equations can 2x1 minus x2 plus x3 is equal to 0 can also be written as x2 is equal to 2x1 plus 6x3. So the vectors x1, x2, x3 can be written as x1, x2 is 2x1 plus 6x3 and x3, which can be written as x1 times 1, 2, 0 plus x3 times 0, 6, 1. So here my vectors are these two, 1, 2, 0 and 0, 6, 1 in a much simpler form than the earlier one. So the eigenspace is span of these two vectors 1, 2, 0 and 0, 6, 1. So here these two vectors are linearly independent. So these two vectors form a basis for eigenspace and hence the dimension of eigenspace is 2. Here we have to observe that these two, this eigenspace and this one, both are same, though the vectors are completely different from one another. Though the vectors are different, the space is same. That means all the vectors generated by these two vectors can also be generated by these two vectors. So different students may get different answers, but all of them represent the same space, same eigenspace. That is to be noted here. And let us prove this interesting statement, interesting theorem, which will be very useful in finding the eigenvalues whenever the given matrix is in a triangular matrix form. So this statement states that the eigenvalues of a triangular matrix are the entries on its main diagonal. So it is very simple and very easy to identify the eigenvalues of a triangular matrix after proving this statement. So eigenvalues are nothing but the entries on its main diagonal when the matrix is in the form of a triangular matrix. So for simplicity, we prove this theorem by considering a 3 by 3 upper triangular matrix. So let us take a 3 by 3 model. Similarly, we can do for a lower triangular matrix, and we can extend this concept to any higher order matrix. So let us consider A is equal to A11, A12, A13 in the first row, 0, A22, A23 in the second row, 0, 0, A33 in the third row. Here we can observe that all the entries below the main diagonal are zeros. So it is an upper triangular matrix. Let lambda be a scalar. Then A minus lambda I is equal to, this is our A, and lambda I is lambda 0, 0, 0 lambda 0, and 0, 0 lambda. So if we subtract this from A, we get A11 minus lambda, and A12 minus 0 is A12, and A13 minus 0 is A13, 0 minus 0 is 0, A22 minus lambda, A23, 0 minus 0 is 0, and again 0 minus 0 is 0, A33 minus lambda. So this is our A minus lambda I. So this scalar lambda is an eigenvalue of A if and only if the equation A minus lambda I into X is equal to null matrix O has a non-trivial solution. So the equation A minus lambda I X is equal to O has a trivial solution, zero solution always. Always we have that solution. If you are able to find a non-zero solution for that equation, then we can say that lambda is an eigenvalue. So let us find that non-trivial solution. If X is equal to X1, X2, X3, then A minus lambda I X is equal to O implies this can be written in matrix form. Here this should be small x. I will correct it. This is small x. So A minus lambda I, this is A minus lambda I, and this is x, and this is O. The equivalent equations are, from the first row we can get A11 minus lambda. If you multiply this one, A11 minus lambda x1 plus A12 x2 plus A13 x3 is equal to 0. That is our first equation. Similarly, the second equation is A22 minus lambda x2 plus A23 x3 is equal to 0. And the next one is A33 minus lambda x3 is equal to 0. So the last one is A3 0 into x1 plus 0 into x2 plus A33 minus lambda x3 is equal to 0. So here it is the third equation. So if lambda is not equal to A11 and A22 and A33, okay, so lambda is different from all these three entries, then x1 is equal to x2 is equal to x3 is equal to 0. Since If lambda is not equal to A33, then from the third equation, this is not 0. So then this must, x3 must be 0. This must be 0. If this is 0, then this part is 0. And if this is not equal to this one, 82 is not equal to lambda 1, this is not 0, then this must be 0. X2 must be 0. Since this part is 0, this is not 0, x2 must be 0. Similarly, x3 is 0 from the third equation, x2 is 0 from the second equation, and it is given that lambda is not equal to a11, so this must be equal to 0. So if lambda is not equal to any one of these three, then x1, x2, x3 all are zeros. That is what represented here. So that is a minus lambda I into x is equal to O has trivial solution only. If all are zeros, then that is the trivial solution, zero solution. If a minus lambda I x is equal to O does not have a non-trivial solution, lambda is not an eigenvalue. So if a minus lambda I x is equal to O has a non-trivial solution, if and only if this is false, that is any one of the entries a11, a22, a33 is equal to lambda. So these three are diagonal entries. So lambda equals to one of the diagonal entries a11, a22, a33. Since lambda is an eigenvalue, so eigenvalues, if lambda is an eigenvalue of A, then lambda equals to a diagonal entry of A. Similarly, we can prove the same when A is a lower triangular matrix. And this can be extended to higher order also. We can prove the same for any higher order matrix. So we can conclude that the eigenvalues of a triangular matrix are the entries on its main diagonal. So for a diagonal matrix, we can easily find the eigenvalues, which are nothing but the entries on its main diagonal. So using that concept, we can easily find the eigenvalues of this matrix 7, 0, 0, 8, minus 4, 0, and 1, 5. So clearly it is a lower triangular matrix. Since all the entries above the main diagonal are zeros. So the entries in main diagonal, these three entries, 7, minus 4, and 3 are eigenvalues. So the eigenvalues of, similarly, the eigenvalues of 5, minus 1, minus 2, 0, 3, 8, 0, 0, minus 2 are 5, 3, minus 2. The entries in the main diagonal. Since it is an upper triangular matrix, all the entries below the main diagonal are zeros. So it is an upper triangular matrix. So the entries 5, 3, minus 2 are the eigenvalues. Let A be an n by n matrix, then A is invertible if and only if 0 is not an eigenvalue. If 0 is an eigenvalue, then the determinant will be 0 and hence it is not invertible. So for this matrix, which is an upper triangular matrix, the entries of main diagonal are 0, 2, minus 1. So the eigenvalues are 0, 2, minus 1. So it is not an invertible matrix. So let us prove one more interesting statement. If v1, v2 and so on Vr are eigenvectors that correspond to distinct eigenvalues lambda 1, lambda 2 and so on lambda r of an n by n matrix A, then the set of v1, v2 and so on Vr is linearly independent. So eigenvectors corresponding to distinct eigenvalues are linearly independent. Here the word distinct is crucial. So eigenvectors corresponding to distinct eigenvalues are linearly independent. That is what we have to prove. Let us assume that our statement is wrong and the set of v1, v2 and so on Vr is linearly dependent, where this v1, v2 and Vr are the eigenvectors that corresponding to distinct eigenvalues lambda 1, lambda 2 and so on lambda. So if they are linearly dependent, at least one of the vector is a linear combination of others. So we can rearrange the set so that we can find some Vp plus 1 such that it is a linear combination of preceding vectors. So I can say that by rearranging the elements of the set if necessary, we can find a least positive integer p such that Vp plus 1 is a linear combination of preceding vectors. So thus there exist scalars C1, C2 and so on Cp such that Vp plus 1 is equal to C1 V1 plus C2 V2 and so on Cp. Since Vp plus 1 is a linear combination of preceding vectors V1, V2 and so on Vp, so we can find scalars C1, C2, Cp such that the relation 1 holds. So let us name it as equation number 1. This is our first relation. And since Vp plus 1 is the first vector which can be expressed as a linear combination of preceding vectors, we can say that the vectors, the preceding vectors are linearly independent since they cannot be expressed as a linear combination of other vectors or preceding vectors here. If it is so, we can take that vector as p plus 1. That vector can be, that p can be chosen instead of this. So as per our choice of p, the first p vectors are linearly independent. Multiplying with a on both sides. So we can multiply equation number 1 with a on both sides. So that we can get a times vp plus 1 is equal to a times this linear combination. That is what written here. So a vp plus 1 is equal to a times c1 v1 plus c2 v2 and so on plus cp. This implies, since c1 is a scalar and a is a matrix, v1 is a vector. So I can write it as the scalars can be taken out, and by distributive laws we can multiply each vector with a. So we can get this one. C1 AV1 plus C2 AV2 plus so on plus CP AV2 on the left hand side. Since lambda k is an eigenvalue for A, for k is equal to 1, 2 and so on R, we have AVK is equal to lambda k Vk for k is equal to 1, 2 up to R. Here lambda 1, lambda 2 and so on lambda R are eigenvalues. So as per the definition, Ax is equal to lambda x. So here lambda is denoted by lambda k here. So Ax is lambda kx here. For k is equal to 1 to up to R. And here x is Vk. So for each Vk, we can write Avk is equal to lambda k Vk. Since Vk is the corresponding eigenvector of the eigenvalue lambda k, where k is 1, 2 up to R. So now I can replace these vectors with lambda k vk's. So using this in equation number 2, we can write avp plus 1 is equal to lambda p plus 1 vp plus 1. That is equal to c1 av1 is equal to lambda 1 v1. av2 is equal to lambda 2 v2 plus so on plus cp times avp is equal to lambda p vp. So here the matrix A can be replaced with lambda 1, lambda 2 and so on lambda as per the vector, as per the corresponding eigenvector v1, v2 and so on v2. So this is our equation number 3. So first equation can be multiplied with lambda p plus 1. If we multiply first equation with lambda p plus 1, we will get this one. Lambda p plus 1 vp plus 1 is equal to c1 times, here we have our first equation. So we are multiplying this with lambda p plus 1. So lambda p plus 1 vp plus 1 is equal to c1 lambda p plus 1 c v1 and so on. For each v, for each vk, we are adding v lambda p plus 1 here. So that is this one. Lambda p plus 1 vp plus 1 is equal to c1 lambda p plus 1 v1 plus c2 lambda p plus 1 v2 and so on Cp lambda p plus 1 v2. Let us denote this equation by equation number 4. And now 3 minus 4 implies, this is our third equation. Now 3 minus 4 implies, on the right hand side we have 0, same vector, so it is 0. On the left hand side, C1, sorry, on the right hand side we have this vector, on the LHS it is 0. C1, here it is lambda 1 V1, the multiple of C1 is lambda 1 V1. So lambda 1 V1 is also taken as common. Here it is lambda p plus 1. In the second addition there is lambda 2 V2. So here it is lambda p plus 1 V2. So after taking V2 as common, we get C2 times lambda 2 minus lambda p plus 1 times V2 plus so on plus Cp times lambda p minus lambda p plus 1 V. So this is obtained from 3 minus 4. Since these eigenvalues are all distinct, that is the crucial point of this statement. It is given that all the eigenvalues are distinct. So none of the factors in the above equation, lambda 1 minus lambda p plus 1 or lambda 2 minus lambda p plus 1 and so on, lambda p minus lambda p plus 1 are 0. So no one is 0, all are non-zeros. And we have already seen that the set of V1, V2 and so on Vp is linearly independent. The first p vectors which are before Vp plus 1. The first p vectors are linearly independent and all these are non-zeros. So to satisfy this equation, so these are non-zeros, these are all linearly independent, V1, V2, Vp are linearly independent, and these entries, these factors, lambda 1 minus lambda p plus 1, and these are all non-zeros. So since this set is linearly independent, all the C1, C2 and so on Cp must be zeros. Otherwise, if at least one of these are non-zeros, then we can say that this system, this equation has a non-zero solution. If this equation has a non-zero solution, we can say that V1, V2 and so on Vp is linearly dependent, but it is not true. Since these are linearly independent, one of the coefficient must be, every coefficient must be 0. If even at least one coefficient is non-zero, then the set V1, V2 and so on Vp is linearly dependent. So every coefficient must be 0, but these factors lambda 1 minus lambda p plus 1 and lambda 2 minus lambda p plus 1 and so on, these are not zeros. So this C1, C2 and so on Cp must be zeros. So we have Ci, in general we can write it as Ci is equal to 0 for all I is equal to 1, 2 and so on up to p. So substituting these values in equation number 1, we get Vp plus 1 is equal to 0 V1. Since C1 V1, C1 is 0, C2 is 0. So we can write it as 0 V1, 0 V plus 0 V2 and so on plus 0 Vp is equal to 0. Since 0 V1 is 0, you know that. If you multiply a vector with 0 vector, you will get a 0 vector. addition of all zero vectors is again a zero vector. So Vp plus 1 is 0, which is not possible. Since Vp plus 1 is an eigenvector. So here V1, V2 and so on, these are all eigenvectors. Eigenvectors are by default, they are non-zero vectors. By the definition itself, these are all non-zero vectors. So Vp plus 1 cannot be a zero vector. So this is a contradiction. This contradiction arises due to our assumption that V1, V2 and so on Vr is linearly dependent. So the set V1, V2 and so on Vr cannot be linearly dependent. So the set must be linearly independent. So this is the proof of this theorem. Let us quickly go through it once again. So if V1, V2 and so on Vr are eigenvectors that corresponding to distinct eigenvalues lambda 1, lambda 2 and so on lambda r of an n by n matrix, then the set of V1, V2 and so on Vr is linearly independent. So to prove this statement, we have taken a contrary statement that the given set is linearly dependent. We are going to prove that this is a contradiction so that we can prove the set is linearly independent. So whenever a set is linearly dependent, at least one of the vector is a linear combination of other vectors. So by rearranging them, we can find a number p such that Vp plus 1 is a vector which is a linear combination of preceding vector. Let that number is a least positive integer so that the first vectors are linearly dependent. So when Vp plus 1 is a linear combination of preceding vectors, it can be written as Vp plus 1 is equal to C1 V1 plus C2 V2 and so on Cp Vp. And the first set is, and the set of first elements V1, V2 and so on Vp is linearly independent. So after multiplying with A on both sides, we will get this one. And since lambda k is an eigenvalue of A, AVK can be written as lambda k Vk. So all these AV1, AV2 and so on, AVP and this AVP plus 1 can be replaced by these lambda k Vks. So after replacing the same, we get this equation number 3. So first equation can be multiplied with lambda p plus 1 and this is the resultant equation. And after 3 minus 4, we get this equation. So in this equation, V1, V2 and so on, Vp are linearly independent. Hence the coefficients, all the coefficients must be equal to 0. Otherwise, the set is linearly dependent. But since the eigenvalues are all distinct, all these factors, lambda 1 minus lambda p plus 1, lambda 2 minus lambda p plus 1 and so on, these are all non-zeros. So these C1, C2 and so on Cp must be 0. So if these C1, C2, Cp's are 0, then from the equation number 1, Vp plus 1 must be 0. But it is not possible, it is a contradiction since it is an eigenvalue. Eigenvalues cannot be, it is an eigenvector. Vp plus 1 is an eigenvector. Eigenvectors cannot be zero vectors. By the definition itself, they are non-zero vectors. So the assumption, our assumption, the set v1, v2 and so on, Vr cannot be linearly dependent, so it must be linearly independent. Thank you for watching.